Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be differentiating implicit functions. So let's get started. So before I define what an implicit function is, I better define what an explicit function is. And this is fairly straightforward. We've seen these functions throughout the entire work on differentiation so far. So in fact, all functions of the form y equals f of x are explicit functions. So what's an implicit function? So all functions which can only be written in the form f of xy equals c, where c is some number, c is some real number, are implicit functions. So it's worth explaining what I mean by f of xy. So what I mean by this is you've got some function, but the function is not really a function of one variable, x, but in this case the function is a function of two variables. So an example might be, say something like this. So you've got x cubed plus 5xy plus y cubed equals 16, right? So here, what we've got is our f of xy is actually obviously the x cubed plus 5xy plus y cubed, and our c is actually, of course, 16. Now, the thing to keep in mind is it's not possible to rewrite this in the form just y equals f of x. So in other words, you might think to yourself, well, I can just go to this and I can manipulate this, rearrange this so that I can in the end write down y is some function explicitly in terms of x. And the point is that's not always possible. And when that's not possible, the function that we actually have to begin with, we call that an implicit function. Okay? I should make a remark here, which is to say implicit functions are a lot more general than explicit functions. So implicit functions, well, what do I mean by that? What I mean by that is, suppose you have an explicit function. So you have y equals f of x. This is an explicit function where only the thing on the left-hand side is y and everything on the right-hand side is something in terms of x, right? So I can actually rearrange this explicit function to write this down. Y minus f of x is actually equal to 0, right? And then I can say define a capital F, and this is now a new function of two variables, x and y, and we take it to be y minus lowercase f of x. Okay? So once we've defined this function, then we can come back here. We can say f of xy is actually equal to 0. And in fact, we can go further and we can go back and say, well, let's take c to be 0. Then I can come to what I wrote down before and actually just put a c here. So what we've managed to do is we've managed to go from, in this case, which is an explicit function, to, in this case, an implicit function. So the point is, we can always do this. So for any explicit function we get given, we can always use this sort of a definition and actually arrive at some sort of an implicit function. However, we cannot always go back, right? So every time I give you an implicit function, that doesn't mean that you can rearrange to actually get an explicit function. And the example I've given above here is the point you've got to keep in mind. There's no way to be able to write that this function in a form where y equals something entirely in terms of x. Okay. So clearly we need to be able to differentiate functions like this, and this is what implicit differentiation allows us to do. It allows us to be able to differentiate these sort of things directly without having to rearrange to sort of get something of the form y equals f of x, which is what we would have done up until this stage. So let's jump in and look at the theory as to how we start to differentiate these sort of things. So in fact, the key idea for implicit differentiation is actually the chain rule, right? So what do I mean by that? I mean, consider this. Consider a function u equals f of y, where y is actually some other function of x, right? And what you might want to do is then you can obviously say that tells us that u is actually a function of x ultimately, but the point is because we have a relationship for y and x explicitly, what we can actually do is it is possible to rewrite the whole thing as some function of two variables. Okay, so perhaps an example here might actually help. So we have an example here. So we can define u purely as a function of y. So I hope you would agree that there are no x's in sight here so far. But then we can define y purely as a function of x, right? So that's completely well defined. The inverse sine function is a very sensible function. And so really, if we wanted, we could go back and write u completely in terms of x, right? So that would be in the form that we've actually got here. However, out of convenience, because if I say y is sine inverse of x, that's the same thing as saying sine y is actually x. And we see that there's a sine y already in the function that we've actually got, which is describing u. Then out of convenience, we can just replace the sine y with an x, right? So we can now write u in a form where it's a function of both x and y. So really we have this sort of a form. So I recognize that perhaps on the A-level syllabus you may not come across too many functions like these, but you know, as you sort of spend more time doing differentiation, these sort of things are quite common, and there's always a question on implicit differentiation in the exam. So if you're not already comfortable with this sort of thing, certainly by the time you get close to the exam, you need to be, okay? So let's continue with the thought that I was actually presenting, which was if I have something which is like this, so u as a function of y, which can be in fact because of a relationship between y and x, which can be written sort of in an implicit form, how on earth do we differentiate this function, right? And the answer is actually you can differentiate this function by effectively just differentiating this function here using the chain rule. So let's do that. So I say chain rule. And I know that du by dx is going to be du by dy times by dy by dx, right? Okay, so if I now think about my u, because I can think of u in lots of different ways, we basically have three different descriptions of u here. So I'm going to use a description that's sort of convenient to me each time. So the first description I'm going to use is use f of y. And with that description, I know that du by dy is actually just f prime y, right? And the second description I'm actually going to use this description here. So I'm going to say if I've got u equals f of xy, then du by dx is actually equal to d of f of xy differentiated with respect to x. So we can actually put these into our chain rule, and I'm actually going to leave the dy by dx term alone because ultimately when we have implicit functions and we want to differentiate them, we still want to work out the rate of change of y with respect to x. So in fact, that's precisely the sort of thing I'm looking for, so I don't want to get rid of that from my chain rule description, right? So let me put in the things I've already got. So I say d of f of x, y differentiated with respect to x is the same thing as f prime y multiplied by dy by dx. And this is the key idea. This is precisely the sort of thing that we're going to keep returning to when we're differentiating implicitly. I should add, this might look sort of difficult and awkward maybe if this is the first time you're seeing this, but it's very easy to use as an idea. And of course, I think looking at a few examples will actually help us understand this a lot better. So let's try and do some examples. So for example one, we actually have a very straightforward looking function. It's in the implicit form currently because we've got some function of xy on the left and just a constant on the right. Of course, this function is easy enough that if we actually wanted, we could rearrange this and write it in explicit form and then go on to differentiate. But given the entire point of the video is to do implicit differentiation, we actually want to differentiate this function implicitly. Okay, so let's have a go at that. And the way we differentiate implicitly is we just come to the function. So I'm going to write down the function and then I'm going to say I want to differentiate everything on the left with respect to x and I want to differentiate everything on the right with respect to x. Okay, we're doing the same thing to both sides of the equation, so that's perfectly well justified. Uh, we also know that when we differentiate functions or things, we can differentiate each part. We've sort of seen that before. So in fact, on the left, I can say I can just differentiate the first term, and then I can say I can differentiate the second term, right? And of course, the right-hand side, when I differentiate a constant with respect to a variable, I just get 0. So now we just have to evaluate these two derivatives and then we're basically done, right? So what's x differentiated with respect to x? Well, that's just 1. And what's y differentiated or y squared differentiated with respect to x? Okay, so this is where we're going to use the thing we saw, which is we saw something like this. So we saw du by dx is equal to du by dy times by dy by dx. Even though we sort of saw it in a slightly more uh, gory form, we saw it in this form where we were saying that actually our u is a function of both x and y. So both those forms I've written down are actually equivalent, right? So in this case, my function of y can just be taken to be y squared, right? And therefore, if I actually come back, apply the chain rule either in that form or in that form, I'm going to have a derivative of f of y go here. Well, what's that going to be? Y squared differentiates give me 2y. But then both these statements tell me that actually my dy by dx has to be there as an aside, right? So I'm going to have to write down dy by dx. And this thing here that we've just now written down, this is basically what's said to be an implicit derivative. Because what we've done is we've actually done a differentiation with respect to x, but we've differentiated something with respect to y, but we also have a dy by dx there to sort of counterbalance the fact that when I wrote that down, I only differentiated with respect to y, so that then ensures that the overall thing is actually a derivative with respect to x. Okay, so really at this stage we're basically done. So now it's just a matter of rearranging this and writing dy by dx explicitly. So I can say 2y dy by dx is equal to minus 1, and of course that tells me that dy by dx is equal to minus 1 over 2y, where I should say y now cannot be 0. So we have our derivative, but let's check our answer. Like, did we get a sensible answer? So let me go back to what we had, and let me actually now rearrange this. And perhaps the easier way to sort of rearrange this might be to say x equals 1 minus y squared, and then I want to find dy by dx. So find dy by dx, but because I've got a function of x in terms of y, I can easily write down dx by dy. Dx by dy is going to give me 0 minus 2y, which of course is just minus 2y. But then that tells me, using a standard result that we've sort of seen lots of times, that dy by dx is 1 over dx by dy, which actually is nothing other than 1 over minus 2y, where of course y is not 0. So we actually have the exact same answer, but we got to it using a very different argument. And even though in this case you might look at this and say, well, it was a lot easier to do it like how we've done it in the remark, and I would agree with you. But the point is we need to exercise our skills so that when we're given implicit functions that we're not able to write in explicit form, then we can still differentiate those functions. So as a means of practice, this is actually it's actually a fair thing to do. So example 2, we have another implicit function and we're expected to differentiate this implicitly. Again, this is one of these things we could write down explicitly, but let's just do the entire thing implicitly. So we want to differentiate the entire left-hand side with respect to x, and then we say, well, that's got to be the same as differentiating the entire right-hand side with respect to x. But of course, at this stage, I noticed that I've actually got a product there. So I've got an x squared and then I've got a y squared. So to be able to differentiate this, I've got to apply the product rule. But to apply the product rule is to say we differentiate the first function and we write down the second function, and then we differentiate the second function and then we write down the first function. So far what I've written there is just a statement of the product rule written out without having to worry about writing out the formula of the product rule. We should be okay with that sort of a thing now. And then differentiating 1 with respect to x is just 0. And now we just have to simplify the left-hand side. So what's the derivative of x squared with respect to x? Well, that's just 2x. So the first term is completely fine. What's the derivative of y squared with respect to x? This is where the chain rule comes in, of course, which is the whole point of implicit differentiation, which is I differentiate y squared with respect to y, and then I multiply by dy by dx. And this is what I was trying to say, which is when you actually come to applying the idea that I wrote down of implicit differentiation, it's a lot easier because you can just look at that and just think of the chain rule directly, and you're home, right? So I'm just going to rewrite this out and I'm going to say, well, y squared differentiates to give me 2y and the dy by dx has to be there, right? And then the x squared just has to be there. So we've essentially got an equation which describes our derivative completely. It's just a matter of now rearranging this to be able to say what dy by dx is. So I can say here, I can say 2x y squared plus 2x squared y is my dy by dx, like this, and then dy by dx entirely is just minus 2xy squared over 2x squared y, which of course is nothing other than minus y over x, where I better say x and y cannot be 0 actually. But of course we already knew that because x and y were taken to be just positive anyway, right? So we've managed to work out our derivative implicitly. As before, let's quickly check our answer. So we might want to start by xy or x squared y squared equals 1 and then rearrange this in sort of explicit form. So if I say I'm going to have xy all squared equals 1, which tells me xy is actually equal to the square root of 1. And because x and y are both positive, then I'm just going to have a positive square root. So I'm going to have xy actually equals 1, which tells me y actually equals 1 over x. And now we have y as a function of x explicitly, so we can just differentiate this. Therefore, dy by dx is actually looking like, because this is going to be x to the minus 1, then dy by dx is just minus x to the minus 2, which is minus 1 over x squared, of course, right? So at this stage, you might say, hang on, we had a very different answer there, and you've got a very different answer there, right? But the point is, we can use this relationship here. Okay, so what can I say? I can actually, it's even better to say this. So let me say that. So I'm going to say that the one on the top, I'm going to replace that by xy, because I know from this relationship here that x times y is always going to give me 1. So I actually end up with this, and simplifying this, I get precisely the thing we actually had before. And of course, I've got to say again that I can't have these things being 0. Example 3, we're given another fairly straightforward implicit function, and we've got to differentiate it, so let's jump in. We're going to do the exact same thing that we've been doing, which is we're going to differentiate the entire left-hand side with respect to x, and therefore we must differentiate the entire right-hand side with respect to x, otherwise the equation wouldn't balance. And when we differentiate the left-hand side, we can differentiate each term. So I just write this down. The right-hand side, of course, differentiate to just give me 0. And then I best differentiate each of these. So x squared with respect to x differentiates to give me 2x, but it's going to be awkward to differentiate y cubed with respect to x. So I'm going to turn to the chain rule and say, let me just differentiate it with respect to y, and then I'm going to write down dy by dx as a way of compensating. This is the implicit differentiation part. part of our calculation. So you could dress this up in lots of ways, as I've already said. One way is to basically say du by dx is du by dy times by dy by dx. Another way is actually to say, well, if I've got some implicit function, xy, and I want to differentiate it with respect to x, that's the same thing as differentiating the y function and then multiplying by dy by dx, right? Where I should say u equals f of xy, and u also equals f of y with y being some function of x. As I've said before, we actually don't have to even think about this sort of thing here in the green, right? We just go to this and just work with it in a much more applied sense. So what I've said here in the green is a lot more pure, sort of raw analytic way of thinking about this, the more technical way of thinking about this, but a more practical way of thinking about this is actually just differentiating the y and then just putting down a divide by dx. And that's how the vast majority of students who actually learn implicit differentiation think about this because it helps them sort of work through problems in a much more easier way. So let's evaluate this. So we still say 2x, but y cubed differentiates to give me 3y squared, and the dy by dx is still there. And now we're done because this equation here effectively describes the relationship our derivative has to satisfy, and we can use that to be able to write down what the derivative has to be. It has to be minus 2x over 3y squared, and y better not be 0, of course. Now, I won't bother with checking the answer in this case. So example 4 is when we start to sort of encounter things when things go up a notch a little bit. I've not even said differentiate this implicitly because quite frankly there isn't really any easy way of differentiating this if you were to choose not to do it implicitly. Because if you look at this function here, you've got x minus y and the whole thing is to the power 4. If you decided to expand this, you will have lots of terms with sort of x and y's mixed up, and so it's going to be practically impossible to be able to write this down explicitly as a function of y in terms of x, right? So really the only option we have here is to differentiate this implicitly. The second thing I should add is, of course, the right-hand side is not just a constant. If I wanted, I could really just rewrite that by saying x minus y to the 4 minus x minus y equals 5. I could rewrite it in this way, but quite frankly, implicit functions are sometimes left with mixed things on the left and mixed things on the right and not just constants, right? Just because it's sometimes a bit more convenient mathematically. So let's not worry about this too much and let's just jump in and start to differentiate. So here's a solution, right? As always, we want to be able to differentiate both the left-hand side and the right-hand side entirely with respect to x. Okay, so there's nothing sort of radical there. But once I've got this, here's the problem. That's a function of both x and y, right? So I'm going to have to use implicit differentiation for that. But also it's a function of a function. So I'm going to have to use the chain rule as well as implicit differentiation, which of course is another way of saying chain rule. So I'm effectively going to have to use the chain rule twice, right? So let me perhaps write this down here. So if I've got something of the form f of x to the n, we've already seen before that to differentiate this sort of thing, we're going to get n f prime of x multiplied by f of x all to the power n minus 1. So that's the first rule I'm actually going to use. But obviously in this case, I should perhaps not have said f of just x. I should have said f of xy maybe. But the point is the rule isn't really going to change too much. So I come here and on the left hand side I say I'm going to have 4 because my n is 4. Then I'm going to have the derivative of this function on the inside. So that function on the inside is basically x minus y, so I want the derivative of that with respect to x. And then I'm going to have this entire function that's there all to the power 1 less than what it was before. So I'm going to have x minus y to the power 3, right? So that's our left-hand side. The right-hand side, we're just going to split this up so that we apply the derivative to each part on the right. And that's fairly straightforward. We can just sort of do that directly. Of course, now when we come to the left-hand side again, we have to differentiate this, and we're going to do the same thing as what we've just done on the right, which is we're going to say we differentiate each part one at a time. Okay, and then obviously the whole thing is being multiplied by x minus y cubed, and we're back again to the right where, well, when you differentiate x with respect to x, you get 1. When you differentiate y with respect to x, and here's the nub, what we can actually do now is we can do two things. You can either say the derivative of y with respect to x is the same thing as the derivative of y with respect to y times by the derivative of y with respect to x. But of course, the derivative of y with respect to y is just 1. So that's just going to give me 1 times dy by dx, right? Which of course is just dy by dx. But on the other hand, you could have just looked at that and said, well, that's just dy by dx because I'm literally differentiating y with respect to x, right? So we would just write that down. We should just say dy by dx, right? And lastly, the last term on the right-hand side, a constant function differentiated with respect to a variable, is just 0, okay? I should emphasize you should find this rather interesting because on the top here we actually applied implicit differentiation effectively in sort of informal terms. But really, implicit differentiation is just consistent, is what we've figured out with the initial description of how we wrote down a derivative, right? So that should be quite reassuring. Let's move back to the left, and we again say the derivative of x with respect to x is just 1. And using the exact same argument we used on the right-hand side here, we say that differentiation actually is just going to give us dy by dx. And we're basically done because we have an equation which actually has our derivative as part of the equation. So now it's just a game of sort of rearranging. So let's do that. So I'm going to say 4 x minus y cubed minus 4 x minus y all cubed times by dy by dx. So that's just me expanding both the 4 into the bracket and this x minus y all cubed into the bracket. And then the right-hand side is obviously what it is. It's just 1 plus dy by dx. And then I can rearrange to say I want to take all this to the right-hand side and bring that 1 to the left-hand side. So I'm going to say 4x minus y cubed take away 1 is equal to 4x minus y cubed dy by dx add dy by dx. And then I can factorize out the right-hand side. So I can say, well, on the left, first of all, I'll have this take away 1, and then I can factorize out for x minus y cubed. I can say plus 1 dy by dx. And now we simply divide, and we get our dy by dx in a very sort of clean way. So we've got that, and we've got 4x minus y cubed plus 1, and that's our derivative. As far as checking this is concerned, the sad fact is it's actually quite hard. And in fact, this is precisely why we needed implicit differentiation, because otherwise we wouldn't even have a way of differentiating this in the first place. Okay, so we can maybe move on to the next example. Example 5 presents us with something a little bit more interesting. In this case, we don't just have to work out a derivative, we actually have to work out the actual value of the gradient at a given point to a curve which is actually given in implicit form. Okay, so before we actually jump in with a solution, we need to understand how we go from sort of a point to being able to say, is it on the curve? So in the explicit case, if we had a point AB and we had a function y equals f of x, what we would do is we would say when x equals a, is y equal to b? And we would put a into the function, and if we happen to do the calculation and get b, then we say fine. If we put a into the function and we do the calculation and we don't get b, then we say no. So in the first case, we say yes, point AB is on the curve. And in the second case, we say no, point AB is not on the curve. So let's think about the implicit case. So suppose we have AB, which is a point, and suppose we're again given a function, but now it's an implicit function, right? And this is describing a curve, and the question is AB on the curve, right? And the answer is actually very, very easy, because what we do is we just go to our function, capital F, which is describing our curve, and we stick in A and B. And when we stick in A and B, these are going to be numbers. We're going to be able to do a calculation and get an answer out. And when we get an answer out, if we get the number out to be C, which is the exact same C that's actually describing our implicit function on the right-hand side, then we can actually come back and say, yes, the point AB is actually on the curve, okay? But if we actually put in A and B, and in this case, if we get a number which comes out which happens to be not equal to C, then we say no. Okay, so that's really the key idea. This is the condition that we actually need to be able to check whether a point is going to lie on a curve or not. So perhaps I need to do sort of little boxes around this just to make sure that we're completely clear that it's these two criteria are completely equivalent. The thing on the left is describing it for the case of explicit functions, and the thing on the right is describing it for the case of implicit functions. With that point now clear, we can now go on and do the example. So let me make a bit of room and we can get started with the solution. So solution, right? We seek dy by dx at 2 minus 3. That's what we seek. So how are we going to work out dy by dx? Well, I just start with this function, which is 2xy, and as before, I differentiate just both sides of it purely just with respect to x. And we know that the thing has to balance because we're doing the exact same thing to both sides, right? Now, the derivative of something like 3 to the power x is a standard derivative. We've already seen formulas for this sort of thing, so it's going to be log 3 times by 3 to the x. And the derivatives on the right-hand side, well, going to be dy by dx, applying to just y, and then take away dy by dx, applying to 2 sort of xy, right? Now, we know that dy by dx is just dy by dx, in other words. So I don't even need to worry about applying the chain rule to that or the implicit formula, the implicit sort of differentiation rule to that, even though I can. But the second thing is I've actually got there a product, so I have to apply the product rule. And the way we do that is we write down the first function, we differentiate the second function, and then we write down the second function and we differentiate the first function. And everything is just differentiated with respect to x, obviously, right? So at that stage, we can actually simplify the right-hand side a lot more, because we can just say, well, this thing here, the derivative of y with respect to x, is just dy by dx. So I just say 2x dy by dx, and then I say y, but then 2x differentiated with respect to x is just 2. So I write that down, and then obviously it's just a matter of tidying things up. The natural thing to do here would be to basically expand out this bracket on the left-hand side and then just rearrange. So we're going to say the left-hand side is going to be log 3 times by 3 to the power x, and the right-hand side is going to be dy by dx. Take away 2x dy by dx, and then take away 2y, no less. Okay, so now taking all the sort of non-dy by dx terms, in particular the negative 2y to the other side, what we're going to have is we're going to have log 3 times by 3 to the x add 2y is equal to, and it's convenient to factorize out the two dy by dx terms to be able to say 1 minus 2x dy by dx. And now we're nearly done because we can write down what our derivative is, which is log 3 times by 3 to the x add 2y, but then the whole thing is divided by 1 minus 2x, right? And of course, x better not be a half. Indeed, we're not entirely done because we want a little bit more than just the derivative. We actually want the gradient at a point. So I'm going to put the numbers in and I'm going to say, well, I just evaluate my gradient at the point x equals 2 and y equals minus 3, and we can sort of stick those in. So we see that it's going to be log 3 times by 3 to the power while x is 2, so it's going to be log 3 times by 9, so I'm just going to say 9 log 3. And then I see that it's going to be add 2y, but my y is minus 3, so 2 times minus 3 is minus 6, so I'm going to put that in. And then the denominator is, of course, our x is 2, which obviously means that we can use the formula in the first place. And when I stick 2 into the denominator, 1 minus 2x, I get minus 3. So I can just put that down. And here we have it. Before moving on to the next example, it's worth doing a check. And actually, I don't want to check necessarily the answer that we've worked out, but I want to check the fact that whether this point here is actually on the curve C or not, right? So I'm just going to say rewrite the equation of our curve in this sort of form, right? And sub x equals 2 and y equals minus 3. So what do we get? We get 3 to the power 2 minus minus 3 plus 2 times minus 3. And what does that give us? Well, 3 squared is 9, minus minus 3 is plus 3, and 2 times 2 is 4, and then times that by negative 3 is actually negative 12. And indeed, that gives us 0. So we've shown that the point 2 minus 3 lies on C. So in other words, it makes perfect sense to ask the question, what is this derivative evaluated at sort of this point? And we can then say with confidence that this number here, when we evaluate it, is going to give us the steepness of the gradient to the curve at the point C. Example 6 gives us a problem which is a fairly standard problem as far as the A-level math syllabus is concerned, which is given a function, find where the stationary points are. Of course, the slight catch in this case is the fact that the function we have is actually an implicit function, and this is a proper implicit function. It's not going to be possible to be able to rewrite this in a form y equals f of x in this case. So we're just going to apply the same sort of ideas. We're just going to differentiate the whole thing. So we differentiate the entire left-hand side as follows, and we differentiate the entire right-hand side with respect to x. But of course, when we do that, we know that the right-hand side just differentiates to give us 0, and the left-hand side we can differentiate each term separately as a standard sort of property of differentiation. The first term here, the 3x squared differentiates to give me just 3 times by 2x, which is obviously 6x overall. And then the second term, we need to apply the product rule, so maybe I can sort of do that now. I write down the first part and I differentiate with respect to x the second part. I write down the second part and I differentiate with respect to x the first part. So that's the product rule applied. And then the last term on the left, I've got to differentiate y squared with respect to x. Well, I can just do that by differentiating y squared with respect to y, and then just multiplying by dy by dx. And then the right-hand side we know is already 0. So let's simplify the entire things, and then we get 2x. Obviously, this term here is nothing other than dy by dx. So I write that down. And then the other term in the bracket, the 2x with respect to x differentiates to just give me 2. So I actually just end up with 2y. And outside the bracket, the y squared with respect to y can be differentiated, and I get 2y. But obviously it's got a dy by dx attached to it, so we've got that. And we basically have our equation for our derivative, right? We just have to be able to tidy this up. So that's what I'll do. So let me just say it's going to be 6x plus 2y plus 2x plus 2y, and then I factorize out dy by dx, and the whole thing is equal to 0, which then tells me that actually my dy by dx is basically negative 6x plus 2y, the whole thing divided by 2x plus 2y. And it's obvious that we've got 2's everywhere, so we can tidy this up a little bit more actually. We can take out a factor of 2, which if I take a 2 out, I get 3x plus y, and if I take a 2 out from the bottom, I get an x plus y, which means the whole thing can be simplified to give me negative 3x plus y all over x plus y. So we have our derivative, and I should say x cannot be equal to minus y, because otherwise the denominator goes to 0. Once we have our derivative, what must we do? At stationary points, we know that the derivative is actually going to be equal to 0, which means that this thing we've got here is actually going to be equal to 0. Well, the only way that a fraction can be equal to 0 is if actually the numerator is equal to 0, okay? Because if the numerator is equal to 0, it doesn't matter what the denominator is, the whole thing is going to be 0. So I'm going to say 3x plus y equals 0, which means y actually equals to minus 3x. And this is the key condition. So all stationary points on our curve satisfy this condition. But obviously, the other thing to keep in mind is all stationary points on our curve also satisfy the equation of the curve right at the top, right? So what can we do? We can say all stationary points satisfy actually this system of equations, which is y equals negative 3x and the initial equation of the curve, 3x squared plus 2xy plus y squared equals 6, right? So we solve these simultaneously. I can literally stick in equation 1 into equation 2. So we say sub 1 into 2, and we get 3x squared plus 2x multiplied by negative 3x plus negative 3x all squared is equal to 6, which is obviously 3x squared negative 6x squared plus 9x squared equals 6, which is nothing other than saying 6x squared is equal to 6, which obviously can be solved to say x is plus or minus 1, right? Right, so now that we actually have a solution for x, we can actually get a solution for y just by going to that. So when I put 1 in there, I get y equals negative 3, and when I put negative 1 in there, I get y equals positive 3. So that is y equals negative and positive 3 respectively, right? The signs here, they do matter. So for the positive x value, I get the negative y value, and for the negative x value, I get the positive y value. And once we have that, we actually have the location of our stationary point. So I maybe want to write it somewhere where there's a bit more room, and perhaps I can write it in a different color. So I can say our answer is stationary points at, so when x is 1, y is minus 3, and when x is minus 1, y is 3. So we've been able to solve the entire question. So for our last example, I thought it's worth considering another very standard A-level maths sort of question, which is we're given some sort of a curve and we're given a point, and we have to work out the equation of the tangent to the curve at that point, right? But obviously the slight difficulty in this case is the function we have is actually written in implicit form, and it's not quite possible to write this in explicit form in this case actually. So let's jump in with a solution. Before we actually start differentiating, let's just check that 0, 4 is on the curve. So to check, we go to the equation of the curve. So I'm going to just rewrite that down. And then I'm going to say, I'm going to substitute x equals 0 and y equals 4. Right, so we can just see that in action straight away. We can say 5e to the 0 times by 4 squared plus 2e to the 0 times by 4, which is the same thing as 5 times by 1 times by 16 plus 2 times by 1 times by 4, which of course 5 times 16, well 5 times 10 is 50, and then 5 times 6 is 30, and 50 add 30 is 80, and 2 times 4 is of course 8, which gives me 88, which is precisely what we have on the right hand side of our of our equation of our curve. So 0.04 does lie on our curve. So with that revelation, let's differentiate our curve. So we want to differentiate the entire thing on the left, which is 5e to the xy squared plus 2e to the xy, and we want to differentiate the entire thing on the right, rightly so as well. But before I sort of mindlessly dive into the differentiation on the left, it's perhaps worth thinking about how this actually comes across, right? So I see that I've got e to the x in both of those terms, so I can actually factorize out the e to the x, right? And I can sort of rewrite this in this sort of way. And of course, now it's a product of just y terms here and just x terms here. So perhaps what I can say is, maybe I'll do it in black. What I can say is the thing that I have on the left-hand side can be much better expressed as 5y squared plus 2y times by e to the x. And the thing on the right-hand side, well, a constant function differentiates to give me 0. And now here we apply the product rule. So I write down the first term. So I write down 5y squared plus 2y. And I differentiate the second term, which is obviously e to the x. And then I write down the second term, which is e to the x, and I multiply by the derivative of the first term, which is obviously 5y squared plus 2y. And the right-hand side for the thing that we actually started with is obviously 0. So this is what I'm working with. Let's just evaluate these derivatives. The first one is very easy because we know the exponential differentiates to just give us the exponential. So we can just write that down. So it's 5y squared plus 2y. And then e to the x, right? But the second one, obviously the e to the x is just going to be there. The second one, I've got to be able to apply the chain rule to this, which is obviously how we've been implicitly differentiating all this time. So what I want to say is I want to differentiate the whole thing with respect to y, and then I want to multiply everything by dy by dx to compensate for the fact that I actually wanted the derivative with respect to x in the first place. So let's differentiate 5y squared. That's going to give me 10y. And let's differentiate 2y. Well, that's just going to give me 2. And obviously the whole thing has to be multiplied by dy by dx. And the right-hand side has always been 0. So we've basically done it. We've just got to now be able to rearrange this to write what dy by dx is. So we come back here and say dy by dx is actually equal to minus 5y squared plus 2y times by e to the x. And the whole thing is over 10y plus 2 times by e to the x. And because the e to the x is actually always sort of positive, it's never 0, we can actually cancel out the e to the x. So we can just sort of do that here. So what we actually end up with is minus 5y squared plus 2y over 10y plus 2. And of course, this derivative is only valid for y is not equal to minus 2 over 10. And we're in luck because the point that we're interested in, y is actually equal to 4, so it's definitely not minus 2 over 10. So we can actually say gradient, which is obviously going to be our m in this case, is going to be dy by dx evaluated at 0, 4. So I can just stick those in. And in fact, in this case, we see that we have no x terms here at all, so I don't even need to worry about what the x value is. I just put 4 into here. So I say 5 times by 4 squared is 16, plus 2 times by 4, which is obviously 8. And the denominator is going to give me 10 times by 4 plus 2, which is obviously the numerator gives me 88, and the denominator gives me 42, which simplifies to give me 44 over 21. But of course, there was a minus there all along for the entire part, so I've got to stick minuses in. Right, so a minus there, a minus there, and a minus there, and we've worked out our gradient. So now we can just go to our equation of tangent. Okay, we know it's going to be of the form y equals mx plus c, where m is obviously our gradient, which we've worked out, and c is y-intercept. But the point is, because our point is actually 0, 4, then we already know what the value of c must be. It has to be 4. So we can just write down, in fact, our equation is y equals minus 44 over 21x plus 4. And we've been able to do this entire question. With that, I'd like to bring this video to an end. We hope you found this useful. Do let us know in the comment section as to what you would like to see more videos on. Please do hit the like and subscribe buttons, and we will see you in the next video.